morning. My name is Michael Mezzatone, president of the Experimental Rocket Propulsion Labs.
My name is Steve Murphy. I'm the director of public relations for the Experimental Rocket Propulsion Labs.
Okay, today we're going to be talking about our project to research the feasibility to design a gaseous propellant rocket engine on the Embry-Riddle campus as a student design team. Okay, now this project, it coincides perfectly with the Experimental Rocket Propulsion Lab's mission of developing a liquid third and fourth upper stage engine. Now we also hope to take our research and apply it to this project. Okay. This project will also provide background information on the engine system that we can later use to apply to help integrate with a launch vehicle to put a small satellite into an upper stage Earth orbit.
I'll just introduce you to our schedule of events. We began this project in October, the start of this semester. Throughout the month of October, we were largely just designing our operating parameters, setting up what our total level of thrust would be, what our chamber pressure would be, figuring out how much performance we can get out of our propellants. Then moving into November, you can see that we actually began our CATIA modeling and some of our structural analysis and our computational fluid modeling. And moving into December, we hope to begin prototyping our design and actually publishing some of our results.
Okay, so as far as our propellants, because we're going to be using a bipropellant engine, that means we're going to be using two different propellants, specifically two gases. For that, we've chosen as our oxidizer to use gaseous oxygen, and for our fuel, gaseous methane. Now, these two propellants currently are gaining a lot of attention in the industry because they do hold a very promising value for future space exploration.
And in order to optimize our propellant combination, we utilize NASA's chemical equilibrium software online. And this software allows us to input some of our basic operating parameters such as chamber pressure, expansion ratio, and contraction ratios. And then allows us to vary the level of oxidizer to fuel mass in order to produce this graph here that you see. And you'll notice that the specific impulse, which is the overall performance rating of our engine, is maximized between an oxidizer to fuel ratio of 2.9 to 2.94. So we're designing our engine around that parameter with approximately 2.91 to 1 oxidizer to fuel ratio. And again, after we took the data collected from NASA's chemical equilibrium software, we were able to come up with some more of our operating parameters just by using some of the equations available through the mechanics and thermodynamics of propulsion systems. You can see here some of our basic parameters. You know, our chamber pressure and our thrust were primarily restricted by the university in terms of safety requirements, but the rest of these were designed around optimizing our thermodynamic performance. And here you can see a CATIA rendering of our actual thrust chamber. This here is the combustion chamber element. And you can see some of our regenerative cooling channels that are actually machined all in one piece of copper bar stock. So here you have the chamber, the converging zone, and then the diverging zone, and this is the nozzle exit. So this is kind of a very efficient way of accelerating some of our propellants to produce maximum thrust. And going into our computational fluid modeling, we use microtunnel, and what microtunnel allows us to do is input all of our operating parameters, and it'll produce a fluid model that will simulate how efficient our nozzle design is. So you can see downstream of our nozzle exit, we have a very large Mach number followed by several large shock waves. So that shows that the engine is actually producing a supersonic flow approximately Mach 5. And here is that simulation visually. This to help you, get a little better understanding of this. This is an axisymmetric plot, cross-sectional area of the nozzle. So what you see here is the center line of the rocket. Over here you would have the actual combustion chamber, and this is the nozzle here. And you can see our rapid acceleration at the center line.
All right, now on to our injection assembly. Now the injector is responsible for delivering at exactly the right ratio the propellant for the system. Now you can see, because it's a gas, that means that we chose two very prominent methods in the industry, such as coaxial injection and showerhead injection. These methods are seen in the explode view. We have our first manifold, second manifold, and third manifold. These manifolds all stack together through the bolt holes, as you can see in this side cutaway view. You can also see that the center coaxial elements perfectly fit around the orifice opening in the third manifold. This creates a turbulence between both propellants that will mix them very efficiently, helping to reduce density spots. Now, when you have density spots in an unmixed gas, that's going to create unnecessary vibration and just make a very inefficient combustion. So by taking these two methods, we've made a very efficient system given our two parameters of using gas propellants. And here you can see an actual explode view of the overall thrust chamber assembly. We have the injector right here, our combustion chamber, and these all fit together through the bolt holes that you can see here. So they will be one tight center piece. And this also right now is our cooling system.
And just to give you a little bit of explanation about how this cooling system will work, this is a sleeve here that will slide directly over the chamber itself. And inside of this sleeve, we're going to pump through a cooling solution, most likely ethylene glycol or some other working fluid. That fluid will be pumped in at the throat where we have critical heat flux, and that will help remove the excess heat from the throat and recirculate the coolant through the entire chamber jacket. Just talking about some of our materials to help meet our operating parameters, we're looking at a 110 copper alloy for the chamber stock. This is a 99.9% pure copper, which has a very high thermal conductivity. The cooling jacket will be made of 6061 aluminum. It's a rather mid-grade aluminum alloy, good corrosion, good strength. The injector,
the injectors we made out of 316 grade stainless steel. Now we chose this metal because it has a very low coefficient of thermal expansion. So what that means for us is that during a hot fire testing of the system, it's not going to expand nearly as much as any other metal would, thus providing a very specific orifice geometry, leading to a very efficient flow.
And also, just to touch on the propellant injection fittings, we'll be using Grafton 300 series stainless. This is some fairly standard material, good corrosion resistance, good strength. And for our test stand, we'll be utilizing A36 structural steel I-beams that we're attempting to recycle from the manufacturing department in the structures lab.
As far as sourcing our materials, now these metals are rather expensive buying them raw stock. So we've chosen onlinemetals.com and MasterCar to price our budget.
We'll be utilizing the Embry-Riddle manufacturing lab to produce all of our parts in-house. Embry-Riddle has a 4-axis Haas vertical milling machine and also a Haas tool room lathe, and this will help us reduce our costs as well.
Okay, so as far as budget, because it is an expensive system, we've broken it down in 3 phases. Phase 1 will provide us with our raw materials and our electronics to get started on the actual system.
Phase 2, we move into the propellant delivery system. I'll be purchasing all of our flow regulators, all of our valves, tubing, and as far as electronics, some additional sensory so we can collect our data for the actual hot fire test.
Which brings us finally to Phase 3. Phase 3 will allow for our propellants to be delivered on-site and actually conduct our testing. Conclusions, we found that there is going to be a considerable budget due to the very high technicality of this project. Therefore, we're trying to outsource and put together further funding. We've also found the importance of safety, because if we don't provide a sufficient safety report, the school will not let us conduct our testing, thus making it no longer feasible. And we've also found a very high need for collaborating with other student groups to manage our workload.
We'd also recommend for future revisions to look into cryogenic propellants just for the added performance, and also we need to research a more flight-ready design in order to reduce weight and increase in overall vehicle performance. As a final note, we do need to pursue external funding to make this project more sustainable for our club, so we're looking to partner up with some industrial partners and also seek additional grant funding from the Florida Space Consortium. And next semester, we actually hope to present our research at some space conferences. The Florida Space Grant Consortium has a conference in Orlando, and also possibly the American Institute for Astronautics and Aeronautics has a conference in Alabama that we're very interested in.
All right, thank you. And as you can see, the sky is no longer the limit.
We'll take any questions at this time.
Okay, let's give a round of applause first. Okay, let's take one question. You guys ran over time, okay? All right, who wants to ask it? Go ahead.
Do you guys have any testing location in mind for now?
We do. There's actually a jet engine test facility at the very end of the flight line. It's near Canaveral Hall, and they test first semester turbine engine. So we've actually gotten the approval to use that for our location on campus. So.
Okay, great. Any other burning questions here? All right. Have you had feedback on what you've been doing, at this stage, or is it still pretty much enough in testing that you haven't had any, real criticism of your model yet?
We've been consulting with Dr. Perel from the Aerospace Department, and he's really supporting our design at this point.
Okay.
We're moving along well, but what we need to do right now is start getting some more feedback from the manufacturing supervisor, Bill Russo. He's going to help us put together our CNC plans because we'll be